Hello viewers. In this lecture, I am going to explain qualitative electrolysis. Okay, nothing but Faraday's laws. Okay. So here the Michael Faraday introduced laws of electrolysis. Okay, to explain the quantitative relationship between the quantity of electric current and the amount of substance electrolyzed or deposited in electrolysis process. Okay, so here that Michael Faraday is introduced two laws majorly, Faraday first law and Faraday second law. Okay, so to give a quantitative relationship between that electricity and that amount of substance whatever we are using in electrolytic cell, how much of it is deposited, that is given by that Michael Faraday. Okay, now let's see the first Michael Faraday first law. Okay, so first law is stating that, okay, so the first law stated that the amount of the substance, the amount of the substance or the weight of the substance, okay, so deposited or electrolyzed is must be directly proportional to the quantity of electricity, so whatever we are passing into that electrolytic cell. Okay, so it is given that first law, the first law is stating that here it is given the weight or the amount of the substance deposited or electrolyzed is must be directly proportional to the amount of, okay, other what are the quantity of electricity we are passing into the cell. So mathematically we are showing with respect of here W is directly proportional to Q. Okay, so W directly proportional to Q. So when you remove that proportionality, we get that a constant. So we are showing that W is equals to ZQ. Okay, so what is the W? Where W is equals to weight of the substance. Okay, so weight of the substance in grams. Okay, Q. Okay, electricity. Okay, in coulombs. Okay, so we are presenting the coulombs. Okay, so where Z is equals to the constant, we are giving a special name, electrochemical equivalent. Electrochemical equivalent. Okay, so the weight or the amount of the substance is directly proportional to the quantity of electricity. Okay, so W is directly proportional to Q. Okay, so here we have that one more also. Q can also express in terms of Q is equals to I into T. Okay, so it is also possible to express that coulombs electricity in ampere seconds. Okay, Q is equals to IT. So where I is equals to current. Okay, so current in amperes. So T, time in seconds. So that's why this mathematical expression is also possible to represent in terms of that W is directly proportional to IT. Okay, or when you remove the proportionality, it is possible to write that W is equals to Z into IT. Okay, so W is equals to Z into IT. So where I is equals to current in ampere and T is equals to time in second. Okay, so now when this weight or the amount is going to equal to that electrochemical equivalent, that means if I pass that 1 coulomb of electricity, if I pass that 1 coulomb of electricity into that electrolytic cell, so then what happens? Q is equals to 1 coulomb, then W is going to become Z. Otherwise, so when I am passing that 1 ampere of current in 1 second, so IT is equals to become 1, then W is equals to Z. So that means the electrochemical equivalent is possible to define. So when we are passing 1 coulomb of electricity or 1 ampere of current in 1 second, okay, so the amount of the substance deposited or electrolyzed is equal to electrochemical equivalent. Okay, so that means where, okay, otherwise if Q is equals to 1 coulomb, okay, Q is equals to 1 coulomb, or I is equals to 1 ampere. Okay, T is equals to 1 second. Then what happened? W is equals to Z. Okay, so the weight or the amount of substance deposited or electrolyzed is going to equal to electrochemical equivalent. Okay, so the first law stating that only that a quantitative relationship between the amount of substance, how much of it is deposited with respect to the quantity of electricity. Okay, so the simple way we are given the amount of substance deposited or electrolyzed is directly proportional to quantity of electricity. Got it? Okay. Now let's see second law. Second law. So here second law states that when we are passing the same quantity of electricity, through the different type of electrolytic cells which are connected in series. Okay, so that means, for example, I am taking one electrolytic cell. Okay, one electrolytic cell is there which have a dilute H2SO4. Okay, so one of the electrolytic solution I am taking that H2SO4 ion. In this one you have two electrodes and I am keeping one more electrolytic cell. So this is containing that aqueous copper sulfate. Okay, one more different electrolytic solution I am taking that. Okay, aqueous copper sulfate. Okay, here also we have two electrodes which are going to act as a cathode and anode. Okay, and I am keeping one more. So in this one I am taking that aqueous silver nitrate. Okay, so aqueous silver nitrate. Three different type of electrolytic solutions. Okay, so these three different type of electrolytic cells I am connected in series. Okay, I am connecting in series. So when we are connecting in series, so with the help of the battery. Okay, so I am connecting in series and I am posing the same quantity of electricity. Same quantity of electricity through the different electrolytic cell. Okay. So now when we are passing that electricity, here somewhat amount of the substance is going to electrolyze it. So those, suppose here that hydrogen is going to, so electrolyzed. Here you can take that maybe copper is going to electrolyzed and here silver is going to electrolyzed. Okay. So the amount of hydrogen and the amount of copper and the amount of silver is equal to that equivalent weights of particular substance. Okay, so that means when we are passing that same quantity of electricity through the different type of electrolytic cell, the amount of substances deposited or electrolyzed, those are equal to their respective, what is that, equivalent weights. For example, if I am showing that the ratio of these weights WH2, WCU, WAG must be equals to, so equivalent weight of hydrogen, equivalent weight of copper, equivalent weight of silver. Got it? So in general formula, if I am writing the W1 is to W2 is to W3, that is equals to E1 is to E2 is to E3. Okay. So generally it is also possible to write W1 by W2 is equals to E1 by E2. Okay. So the relation I am giving here, W1 by W2 is equals to E1 by E2. From Faraday first law, W is equals to ZQ. Okay. So W is equals to ZQ. So here I am writing that W1 is equals to Z1Q. Okay. W2 is equals to Z2Q. So why you are not taking Z1Q and Z2Q? Okay. So why? Because we are passing same amount of electricity. Okay. I am passing the same amount of that electricity. So why you are representing with the Z1 and Z2? So Z1, Z2 is the electrochemical equivalent. It mainly depends on that whatever the electrolytic solvent whatever we are using here. Okay. So different type of electrolytic solutions are containing different type of electrochemical equivalent values. So that's why I am representing that W1 is equals to Z1Q and W2 is equals to Z2Q. From here what you get, that Z1Q by Z2Q is equals to E1 by E2. So from here again it is possible, right? Z1 by Z2 is equals to E1 by E2. Okay, so this is also one more relation we are given with the help of second law. Okay. Z1Q by Z2Q is equals to E1 by E2. And it is also possible to write in a manner with respect of their Z1 by Z2 is equals to E1 by E2. Okay. Z1 by Z2 is equals to E1 by E2. So that means it is also possible to write Z directly proportional to E. Z directly proportional to E. So when you remove that proportionality, we are showing with that one more constant that I am writing, that E is equals to F Z. Okay. So E is equals to F Z. So what is the F here? F usually we can call that Faraday. Okay. So F is equals to Faraday. So usually 1 Faraday is equals to 96,500 coulombs. Okay. So from here I am writing that F is equals to E by Z. Okay. So F is equals to E by Z. So when you are writing with respect of the first law, what I am given, W is equals to ZQ. Okay. So here it is also possible, right? Z is equals to E by F. Z is equals to E by F. Okay. So Z is equals to E by F. I am going to introduce that Z in terms of the Faraday. Then what is that? W is equals to ZQ from Faraday first law. It is going to become W is equals to E by F into Q. Otherwise, Q is equals to, you have in the formula I into T. So W is equals to E by F into I into T. Okay. So these are the first law of Faraday. We are given with a different type of, okay. Now see that E by F into IT. Okay. So here when you represent in that Faraday is equals to, I am given 96,500 coulomb. Okay. It is also possible, right? W is equals to E by 96,500 coulomb into Q. Okay. Or W is equals to E by 96,500 into I into T. Okay. So these are the two formula. And E is equals to equivalent weight. Okay. So when you are writing with that molecular weight or atomic weight, okay, it is also possible to represent with the help of that molecular weights are equivalent. So what is the equivalent weight? Equivalent weight is equals to molecular weight by n factor or atomic weight by n factor. So possible to represent or not? So W is equals to E by 96,500 coulomb. Nothing but here I am writing that atomic weight, okay, or molecular weight by n factor. By n factor. Okay. So into Faraday into Q. Okay. Otherwise, here also it is possible, right? W is equals to atomic weight or molecular weight by n factor into Faraday into I into T. Okay. So these are the different type of mathematical expressions we are utilizing to identify the weight of the substance deposited or electrolyzed in electrolysis. Clear?